So when you stop, just don't forget to activate your camera and microphone just before you start. Just not right now, but when you're ready. Yeah.
I know you guys used to with like one or your swap or your title. These ones, entire one, now people it's like one map where you try to do like a time series. So we can I made it. And you're good. And if it is for I think I'm going to you would be ordered. You don't know that. I'm just practice. Still up. Oh, it's an adapter for the US club. For that, or else it won't. Yeah. Everyone else that it's new and new. Yes, I think.
Sorry?
You can share your screen and then if you want.
Shares.
Not share
video.
Yeah, the video
Yeah.
and the audio.
Audio should be there.
Already?
It's not turned on.
Yeah, this one, I mean, like online, you have two mics.
Yeah.
So one is for online and this one is not turned on. So just on the Zoom call, you have like the mic and the camera and just.
Yeah, but this is on.
Oh.
It has,
Oh,
if
okay. Okay, very good then. Perfect.
Okay.
Thank you.
It's 9. I think we can start, right? Great, thanks. So, hello everyone, nice to meet you. I am Marcus. I am one of the research software engineers at 52 North. And yeah, today I'm here to speak a bit about open reproducible research. But why do we actually care about open reproducible research? Because, well, research is already great. Science is great. Because of science, we have these tiny little pocket computers, also known as smartphones. And because of science, we know that blowing CO2 into the atmosphere is actually not a very good idea. And because of science, we know how to deal with pandemics. So yeah, science is great. But science is great because there are some fundamental underlying values. For example, just to mention a few, so everyone should be able to understand scientific findings and how we came to these scientific findings. So science should be transparent. But science is done by humans, and humans tend to make mistakes from time to time. So science should be also verifiable. But science is also very, very expensive, particularly when it comes to data collection or when implementing software. So science should be also reusable. But what if I told you that these scientific values are not fulfilled to full extent? So science is not as transparent as it should be. Science is also not as verifiable as we want it to be. And science is also not as reusable as it could be. But what if I told you that there is actually a way to increase the transparency, verifiability, and reusability of research results? And this way is called open reproducible research. I hope that by the end of this lecture, you will be able to articulate what open reproducible research means. I hope that you will understand which obstacles make open reproducible research difficult. And I hope that you will also be able to apply open reproducible research principles to your own work in the future. And finally, I hope that you will be able to choose some appropriate tools to publish open reproducible research. So we will start with a brief introduction into open reproducible research. We will then talk a bit about something that is called the reproducibility crisis. We will also check some obstacles that impede open reproducible research. And then I would like to give you 5 recommendations to get ready for open reproducible research. And these recommendations are not only relevant in academia, but also in industry. And I will also give you some principles and best practices that are more relevant in academia. We will also have a little practical in between. I would like to show you something on the screen. And then we will conclude with some opportunities that come with open reproducible research. All right, let's start with the introduction. So what you see here is the research cycle in a nutshell. It's a very simplified one, but we usually start with the research question or with a hypothesis, and then we design a study to answer the research question or test our hypothesis. Then we collect some data, we analyze the data, we store the results somewhere, and we also write a report, so in which we describe the hypothesis or the research question. We describe how we designed the study, how the study looks like. We designed how we collected data, how we analyzed the data. We add a bit of conclusions, discussions, interpretations, and that's a scientific paper. And this is what we are going to submit for peer review. If everything goes well, the paper gets accepted and it's getting published. If it's getting rejected, then we have to improve the paper a bit. We have to resubmit, maybe to the same journal or conference, maybe to another one. So this is how science works. And once it gets published, it can be reused by others to answer new research questions or to test new hypotheses. During this research cycle, we have quite a few scientific outputs. I highlighted 3. We have the data set, we have the analysis, and we have the paper. I would like to ask you, what do you think is the most important one in science? What is the most important research output? Is it the data, the analysis, or the paper? You can be honest.
Data.
A lot of these?
Data.
Data?
Data.
Okay. Other opinions?
Analysis.
Analysis?
I'll go outside of your options and say the research questions are
The research question, sure. So we had all 3 now. So some people might say it's the paper, some people say it's the analysis. And this is also reflected in UNESCO's definition of open science. So by the end of 2021, UNESCO released a definition for open science. And this definition has 4 pillars, and one of them is open scientific knowledge. And as you can see in this figure, open scientific knowledge is not just a scientific article. So traditional researchers would probably say the most important research output is the scientific article, because this is how we communicate research results. This is what is important when it comes to research evaluation, promotion, tenure, and all that stuff. It's often the number of publications and where you have published them. But in this definition, it's different. It's not just a scientific article. Open educational resources are also important. Open research data, we heard that. The analysis is also important. So this, the open source software and source code, hardware, but it's still also the scientific article. So it's not just the paper anymore that is important, but there's a shift of the focus from the article to the other research materials that are also relevant. But open science is a bit more. I don't want to go into detail because today we would like to talk about open reproducible research, but just to complete the definition, it's also about open science infrastructure. So if we expect researchers to publish open reproducible research, then we also need to provide them with the repositories where they can store the data. We also need to provide them with the computational infrastructure where they can use open source software. Open science also has some societal components besides the technical stuff. It's also about the open engagement of societal actors in the form of citizen science and participatory science, and also the open dialogue with other knowledge system holders and producers, such as indigenous people. So as I said, traditional researchers would probably say something like, well, it's a scientific article that is the most important output because this is the main way how we communicate research results. And I wouldn't even say this is completely wrong, but this is just one half of the truth. Because an article about a computational result is advertising, not scholarship. The actual scholarship is the complete set of instructions which generated the figures. This is also known as Claerbout's claim. And this is particularly relevant in computational research. So I don't see computational research in a narrow sense. It's not about informatics. It's about every research area that relies on research data and source code of software. We could say, well, let's just describe the source code or the analysis in pure text in the article. This is part of the methodology. The methodology should explain what has happened in detail. But you could ask the question, well, is it possible to describe a computational analysis in pure text in such a detail that it is concise and understandable? The problem is that most modern science is so complicated and most journal articles so brief, it's impossible for the article to include details of many important methods and decisions made by the researcher as he analyzes his data on his computer. That's what Ben Marvick said in his article, How Computers Broke Science. So the title already tells a lot. And finally, in the next years, you might even not be able to publish results that are not reproducible. At the moment, it's probably still working. If you publish research results that are not reproducible because you don't add your code into your data, it's often still working. But this is changing. So Philip Stark stated in Nature, from time to time over the past few years, I've politely refused requests to referee an article on the grounds that it lacks enough information for me to check the work. So what all these statements have in common is basically a shift from the scientific article to the other research materials that are also relevant. So the source code, the software, and the data. And it's also about achieving something that is called open reproducible research. But what does it actually mean? Reproducible research refers to achieving the same data, the same results, for example, the tables, figures, and numbers, as reported in the paper, by using the same source code and data. In open reproducible research, these materials are publicly accessible. There are terms and concepts which sound very similar, but mean something different. For example, replicable research, which refers to coming to similar conclusions based on the same analysis, but newly collected data. Okay, then you can ask the question, so what is more important? Is it reproducibility or is it replicability? I don't even think that one of them is more important. I don't even think that this discussion makes much sense because both concepts are essential for scientific work. So research results are reproducible and replicable. Imagine you want to replicate a study. So you take an analysis that was carried out by someone else, you collect new data, and you achieve results that are not consistent with the original results. So what can you do? A first step would be to look into the original analysis and see if it's reproducible, and if there is any kind of error. So both concepts are important to achieve transparent, verifiable, and reusable research results. It's getting a bit more complicated because there's not just reproducibility and replicability, but there are two more concepts. One of them is robustness, which can be achieved by, I have to look it up, using a different data set. Results can be robust if you can achieve consistent results using the same data, but a different analysis. So it's the opposite of replicability. And if you can achieve consistent results using newly collected data and a newly implemented analysis, then the results are even generalizable. Of course, in replicability, robustness, and generalizability, we cannot expect that the results are exactly the same as we would expect it in reproducibility. And even in reproducibility, we have some space when it comes to achieving exactly the same numbers. But in this lecture, I would like to focus on reproducibility. So reproducibility is about achieving the same results using the same data and the same code. That sounds a bit like it's the easiest of the four concepts. It also sounds a bit like reproducibility is a binary concept. So it's either reproducible or not reproducible. But we shouldn't be too strict about that. So what we see here is the reproducibility spectrum. It starts with the publication only, which means it's not reproducible. We don't have access to data and code. You can make one step in the right direction if you provide the source code. But in the ideal case, you also have the data set, so code and data. Even better is if you put the data and the code in a repository and link to it in the paper. And linked and executable code and data is also needed to achieve replicability. So this also shows again that reproducibility and replicability are both important concepts. Let's highlight some lessons learned until now. So the source code to run the analysis and research data are as important as the scientific article. Open reproducible research is about achieving the same results using the same data and source code. Reproducibility is not necessarily a binary concept, but there are steps in between. And there are also different concepts like reproducibility, replicability, robustness, and generalizability, which go into a similar direction but mean something different. So now that we know what open reproducible research means, why is unreproducible research actually a problem? And this brings us back to our scientific values. So if research is not reproducible, it's not fully understandable and easily understandable. I mentioned already that it might be quite difficult to describe the computational analysis in pure text in an understandable and concise way. So if this is not possible, then providing access to code is certainly at least a shortcut, because papers are often limited. The analysis is also not verifiable if the research results are not reproducible. So all that reviewers can do is to read the text, to read the scientific article, to read the methodology and so on, and then they need to make a decision. But they cannot fully understand the analysis if they don't have access to the code, so they cannot verify it. They cannot see if the results are reproducible. So all they can do is trust the results. And trust is actually not a very good indicator in science. But I have to admit that if you have access to code and data, it does not mean that you actually find the errors in the analysis, because source code is still very complex. And it takes quite a lot of time to review source code. And it takes already enough time to review scientific articles. So we cannot expect reviewers to also investigate the source code. And finally, the analysis is not reusable if the research results are not reproducible. This is also a waste of money and also a duplication of efforts. So researchers are often paid for public money, so we should exploit this money as much as possible. But it's also a waste of opportunities for collaborations and credit. So if you publish your source code and your data, then others can reuse it, they can build on top of that, and they can continue your work together with you. So unreproducible research has a number of issues and problems, but there are also quite a few incentives. And these are called the 5 selfish reasons to do reproducible research. Reason number 1, reproducibility helps to avoid disaster. So as I said, in unreproducible research, it's quite difficult to find errors. And reviewers might oversee errors, and this can mean that we publish at the end wrong scientific findings. And this can have quite severe implications. So in medicine, this can mean that a patient receives the wrong dose of a drug, for example. In climate or in the geosciences, it's not so life-threatening. But if I think about climate change, for example, but many decisions are made on scientific findings, and if the scientific findings are wrong, then the decisions might be as well. And this is particularly crucial if we consider the current trend in society that scientific findings are often denied. And if we publish flawed scientific findings, then this makes it even worse. Reason number 2, reproducibility makes it easier to write papers. So if you write a paper based on a computational analysis, then there are some parameters. Maybe you want to change these parameters, you want to try out different settings, maybe you want to try out a different data set, and this is of course easier if the results are reproducible. Reason number 3, reproducibility helps reviewers to see it your way. So how you analyze the research data. So scientific articles are a good way to communicate or summarize the research findings, but they are not so good to explain the computational details. And by having access to reproducible code, they can better understand how you analyze the data. And reason number 4 is reproducibility enables the continuity of your work. So if I think about PhD dissertations, cumulative dissertations, the papers often build on top of each other. It's not like you write one paper and then you go to the next one, and there's no connection between the two papers, but they often build on top of each other, and that's also easier if the results are reproducible. And reason number 5 is reproducibility can help you to build your reputation, because you have nothing to hide. You publish the research results in an understandable way. You invite for collaborations, you share, and this is good for your collaboration and can even result in collaborations with others. So unreproducible research has a number of consequences, and reproducible research has a number of incentives. Then it would be actually pretty surprising if open reproducible research would not be common practice, right? But it is not common practice. In 2016, Monia Baker published a paper in Nature about a reproducibility study. She asked more than 1,500 researchers if there is a reproducibility crisis. 38% said, yes, there's a slight crisis. 52% said, yes, there's even a significant crisis. So in total, 90% think it is not possible, or at least very, very difficult, to achieve the same results by using the same source code and data. This is quite a high number, but how is that possible? We just said that reproducibility is probably one of the easiest concepts. It's just about achieving the same results using the same code and the same data. That doesn't sound so difficult. There are a few reproducibility studies. In the article, Artificial Intelligence Faces Reproducibility Crisis, the authors checked 400 papers from the area of artificial intelligence. Just 6% included source code for the paper's algorithms, 30% included test data, and 54% included pseudocode. So pseudocode is just an abstract description of the algorithm. So reasons for these numbers are different. Some said, well, the source code is work in progress and not yet ready to publish, which is a bit strange. So the paper is ready to publish, but the source code isn't ready to publish. Okay. Some said it's not allowed to publish the source code because the source code is owned by the company. And this is a bit of a tricky issue. So some researchers work together with companies, and then we have to see who is paying for the research. Is it a company? Well, then there's nothing that we can do. They can do with it whatever they want. But if they are paid by public taxes, then it should be a public good. Some want to keep the competitive advantage because they don't want to publish materials and then they fear that others publish the scientific article earlier than they can, so they don't publish the materials. Which shows again that apparently the scientific article is much more important than the data or the code. And it's questionable if the university is the right place to have a competitive environment. Others say that the code was stolen on the laptop. Some people said that the materials were lost or are on a broken hard drive. That issue exists in so the authors of this paper checked 346 articles for the availability of source code used in the paper. In only 27% of the cases, the source code was available. It's interesting that in 79%, the paper was accompanied by data. What can I do?
I don't know.
Okay.
What did you do?
I don't know.
Yeah.
By data.
Sorry. I don't know what to do. Maybe just check here. Sorry. Check the box.
Better?
Yeah.
I think it's better.
Sorry.
No problem. Okay, so in 79%, the articles were accompanied by data.
The camera should be fine, and then you share your screen. The PowerPoint or yeah.
Yeah, I haven't.
Sorry. Yeah. And that should be good. Yeah. Yeah, this is perfect.
Good.
Thank you very much.
Okay, thanks. So, is the data more important than the code? Of course not. Well, the analysis is some kind of the context of the data. And you cannot say that one is more important than the other. That's what we also found out at the beginning. So it's about the scientific paper, the research data, and the source code to run the analysis. The three components belong together. You cannot just separate them. And all three are needed to achieve the scientific values that we mentioned at the beginning. So transparency, verifiability, and reusability. So if we have access to source code and data, does that mean that we have reproducible research results? If this would be the case, then this lecture would be probably over in a few minutes. But I also did a reproducibility study in the geosciences. So I investigated 41 papers that had source code in R and data attached. And I checked for executability and reproducibility. So I wanted to find out whether I can achieve the same results on my local computer. So what do you think? How many papers of the 41 were reproducible? 10, 2, 5, 10, 5, 0. Oh, that's pessimistic. Where 0 is actually quite close, but we had the right answer over there. It's 2. 2 out of 41 papers were executable and reproducible. So when I tried to rerun the code, I had several technical issues. And there were several content-related differences, several technical issues, but more on that in a bit. But we can conclude for now that reproducibility is not common. And it's not specific to a certain research discipline. It's in fact an issue in chemistry, biology, physical and engineering, medicine, earth and environment, and some other disciplines. So basically in every research area that relies on research data and source code. But it's not just a problem that the researchers fail to reproduce someone else's results. It's also an issue that researchers fail to reproduce their own results. And this is a bit strange, right? How is it possible? So what is the problem? So why are so many research results not reproducible? So why are so many, I will come to that in a bit. So why are so many research results, so why do so many researchers fail to reproduce someone else's research results? And why do so many researchers fail to reproduce their own research results? So what we know already is that source code and data is missing. We also know already that peer reviewers cannot check the source code. So they cannot check for reproducibility because they don't have the time, or maybe they don't have the skills. So what can we do in this situation? Well, the answer is pretty simple. It's better teaching. And that's why such summer schools are also a very, very good idea. Some lessons learned from the reproducibility crisis. So reproducibility is needed to get transparent, verifiable, and reusable research results. Reproducibility is beneficial for everyone, but also for yourself. Remember the 5 selfish reasons. Many research articles do not have the source code and data attached, but even if we have access to the data and the source code, it does not mean that the research results are reproducible. An open question is, are unreproducible research results actually wrong? Probably not. Maybe. We don't know. We cannot check. We don't have access to the materials. So we simply don't know. The opposite answer would be, are reproducible research results necessarily right? Well, this is probably not the case. Well, it's at least we can check that. But also let's check some concrete obstacles in unreproducible research. So there are basically 2 categories: missing materials and results that are not executable or not reproducible. Let's start with the first one. A typical argument is working reproducibly costs too much time. And this time is needed to publish scientific articles. But the paper and the source code to run the analysis belong together. That's what we found out already. And this is also shown a bit in the following figure. So in the peer review process, you submit your article. And well, if you publish it the way that I do, then you usually get it back. It's usually getting rejected. So either with minor revisions or with major revisions. And there might be some questions, comments, and these might be related to the analysis. So it's not unlikely that you need to rerun the analysis. And then it will be submitted, and then you might get it back again. Then you have to redo the analysis again. And at some point, you might get published. If you consider reproducible research from the beginning, it's more like a relocation of time. So you spend a bit more time at the beginning in the analysis, but you save time during peer review. So you can resubmit earlier. So at the end, the argument, it costs too much time, is probably not correct. The second issue is why is source code often not executable or reproducible? I mentioned that I did this reproducibility study with the 41 scientific articles. So I searched for papers that had R code and data attached. I downloaded the materials on my local computer. Then I tried to execute them. And I wanted to check, well, are the results executable and do I get the same results as reported in a paper? This is not as easy as it sounds, because only 2 out of 41 articles were actually reproducible. So what happened to the rest? I classified the technical issues that I had into 3 categories. First of all, there were minor issues. Minor issues are rather easy to solve. In this case, I just got an error because the library that was used in the script was not installed on my local computer. It's not a big problem, right? You can just install a library with a few clicks. But if you have one minor issue, you install one library, then you miss another library, you again have to install it. And if you're under time pressure because you have to review an article, several minor issues are also a big problem. But it's not just that I had minor issues, but also substantial issues, which require a bit more effort. For example, this one. A very common and typical error is a wrong file directory. So in this case, I had a file directory C:users:\m and so on. So it's just an example of my script. And this one only works on my computer. Of course, that's my name. And it's also very platform dependent because it starts with C:, so it works on Windows, but not on Ubuntu. It's much better to go for relative paths instead of absolute paths. And this will resolve the error. So these are substantial issues which require a bit more time. You need a bit of programming knowledge, I would say. So you need to be able to read error messages to find out where the error is. You need to correct that. And then you can continue. It doesn't take too much time if you have the experience, but imagine you have 10 of these mistakes, then you will probably not continue at some point. But the real pain came with the severe issues. And these require quite a lot of time, a lot of knowledge about the programming language, and also understanding of the source code. I had one example error, which was cannot open file data ABC CSV because there was no such file or directory. It's a very common mistake, but you have to find out how to resolve that. First, I checked, okay, was the file somewhere available in the folder? And there's just, again, a wrong file path. This was not the case. I also checked the source code if there is some kind of a code snippet that creates the file. But this was also not the case. Then I contacted the authors. I wanted to ask them if they have an idea how to resolve this issue. And what happened is I got a missing source code snippet that produced a file. So in the original script, the source code snippet was not there. One solution to overcome such issues is to ask a colleague to run your analysis. And this is something that we would also like to try out tonight in the reproducibility hackathon. So if you have some time after dinner from 8 onwards, then we could meet here and we could try to reproduce each other's analysis. So you can give your analysis to someone else, and this other person can try out your analysis and see whether the results are executable and reproducible. Because if the results run on one other machine, then it's not unlikely that the results will also run on several other machines. There is also a fourth category of issue, which is the computational environment, but I will come to that later. So after I managed to get the code running, I compared the original results with the reproduced results in a side-by-side manner. And this is one example. So on the left, you can see a screenshot from the original paper, so the map. And on the right, you can see the reproduced figure that I got when I ran the code. And I highlighted some of the differences. In In the orange rectangle, this one, we can see that there are no national borders. But these national borders exist, these national borders do exist in the original map. You cannot see it here on the screen, but you can probably see it in the slide, I guess. So I put the slides on Mattermost. So there you will be able to see it. So what I just want to say is that in the orange rectangle, there are no national borders, whereas in the original, there are some. In the blue rectangle, the scale bar is on the right of the map. In the original map, it's below the map. Maybe I'm a bit too fussy, right? Because these are just design-related differences. So who cares about the design? Well, I almost would agree with that. It's more important that the actual numbers, that the results are the same. But if the design is different, then it's also quite difficult to compare the research results and to check whether they are the same. If we take a look at the yellow rectangle, we see that there are 5 classifications, whereas in the original one are 7. So this is also already a significant change. And in the green rectangle, we see 2 dots that do not exist in the original map. So the actual numbers are also different. So am I still too fussy? I don't think so. I think this is quite a problem. But why is that? Do you have any ideas? Why are the 2 maps not identical? Let's not discuss the design-related issues, but the actual numbers. Do you have an idea? Sorry?
They tweaked their data for the results.
I didn't get it.
They changed their results to make it more favorable.
Ah, you mean they modified them and manipulated them?
Yeah.
Okay,
Maybe.
that's a potential problem. Anyone else?
Numbers on the color bar are different, right? There's until -2 and this is until -0.5, so the colors are different. Maybe also the content is going to become different.
Mm-hmm. Okay.
Maybe the figure that they produce and the code that they send was not like not 1-to-1.
Maybe the code was not the right one, right? Sorry?
Maybe they don't send us. I see.
Ah, yeah. And you?
They could have just like scaled it by a constant or added a value or something to get it within a certain range for plotting.
So I hope you don't expect an answer from me because I don't have one. I'm sorry. All we can do is we can only speculate, because I also contacted the authors again. I asked, so do you have an idea what went wrong? And they were also surprised. They had no idea what went wrong. And I believed them. So I don't think that there was some kind of a bad intention behind that. I guess they somehow played around with the parameter settings. Maybe they lost track at some point. Maybe they changed the code after they inserted the figure in the paper and forgot to update the figure afterwards. Maybe they changed the code after they published the paper and I just downloaded a newer version of the code. All that is possible, we simply don't know. But they provided access to data and code, which is more than the average researcher does, which is why I also don't blame the researchers for that. It's just that there are technical difficulties that were not considered. Some lessons learned. So technical issues are of different complexity. There are minor issues which are easy to solve and require less time. There are substantial issues which require knowledge of the programming language, but are also rather easy to solve. But if you have a bunch of minor and substantial issues, it's unlikely that reviewers will check the work. There are severe issues which require knowledge of the programming language and understanding of the source code. And reproduced figures can have differences related to the design and the numbers. So being aware of these issues is quite important to achieve reproducibility, because I don't think that the authors made these mistakes intentionally. I'm not even sure if they have made any mistakes, because they provided access to code and data, which is, again, more than the average researcher does. But we have to be aware of these issues, because we shouldn't just publish open reproducible research for the sake of open reproducible research. There's an idea behind that. And this is to have transparent, verifiable, and reusable research results. Otherwise, we don't need to invest so much time. So I would like to give you some concrete recommendations to get ready for open reproducible research, which are not just relevant in academia, but also in industry. First one is use open source software instead of commercial software. Commercial software costs quite a lot of money. So we are in a fortunate situation that we have quite rich universities, and we will probably not be in such a situation, but there are quite a few people or researchers in low and middle income countries who don't have the money to pay them. And open science is also about leveling the field. So everyone should have the same chances and equal opportunities. So let's use open source software. One example is to use OpenStreetMap instead of Google Maps. Where Google Maps, you don't have to pay to use Google Maps, but you probably pay with your private data. And it's also not licensed under an open license. So you cannot just reuse, modify, and redistribute the source code used by Google Maps. You can only use it. And OpenStreetMap, it's different. Everything is open licensed, and you can do with it whatever you want. Another example is, of course, ArcGIS. QGIS is the open source alternative. And if you are looking for a tool for literature management, then Mendeley is probably not a preferred option. It's better to use Zotero. And the best thing behind open source software is that it's not a niche topic. So there's quite a rich and big community behind open source software. I don't know how much time I have spent on Stack Overflow to look for programming errors. But if you're dealing with software, then this is probably the place to be. My second recommendation is learn a scripting language. So if you want to analyze data, you basically have the choice between two kinds of software. So you have scripting languages like Python and R and some others, but you could also use point-and-click software, commercial point-and-click software like Stata, SPSS, and Excel. So if you are in a hurry, so you have a deadline and you have to present results, then you might be tempted to use one of these point-and-click software because they are easy to use. You don't need any programming, they are quick, but they will not help you to publish open reproducible research. So it's definitely more important to switch to programming languages like Python and R. And a great advantage of source code scripts is that they contain every single step of the workflow, including data manipulation, processing, analysis, visualization, and so on. It's also important to use scripting languages to avoid manual data manipulation. So you shouldn't do data manipulation in Excel when it's about removing lines, transforming data, and so on. All that should also happen in source code scripts. And if you spend some additional effort into writing scripts like naming files properly, naming variables and functions properly, then you can almost have some kind of a narrative in the source code script. So it's a human readable version of the workflow, so to say. And others can understand it much easier. And this other person can also be you in 6 months. So your future you, so to say, you will probably not remember what you have done 6 months ago. So if you document your research in a proper way, then this will be very helpful for yourself. And you don't have these advantages with point-and-click software. So this kind of software is not reproducible. So you cannot communicate your results effectively and your approach effectively. And you also cannot change the algorithms that are used in these tools. So you don't have any control over the algorithms. So to conclude, scripting languages are the preferred option when it comes to analyzing data. So even if in the future you are in a rush, you should stay with scripting languages. Third recommendation is learn a computational notebook format. So if you learned one of these scripting languages like Python or R, then the step to Jupyter Notebook or R Markdown is rather small. They are pretty easy to learn, but they are very powerful. So this is a nice way to achieve reproducibility. And this is one example. So for those who have not worked with computational notebooks yet, a computational notebook is basically a computer file containing code and narrative text in a single reproducible and shareable file. And this is an R Markdown file in an RStudio programming environment. And as you can see, it mixes source code and text in one file. So Markdown is basically a markup language which is also very easy to learn and follows the what you see is what you get logic. And in RStudio, you can execute these Markdown documents and get a PDF document, which also contains the source code, the text, and the outputs in a single document, which is why we also call these documents executable documents. And I don't know if this is really the case, but such a computational notebook might have helped to avoid the issue regarding the two maps. But I cannot give you a proper introduction to computational notebooks. There are some learning materials which are very helpful. You can look at them later. Then you should also learn a collaborative software development tool. So it's likely that you will not work alone in the future. So you will work with others. And one very famous collaborative software development tool is Git, which is very popular. And there are also two web applications that build on top of Git, which are GitHub and GitLab. And these tools, I also use them. So they are very, very helpful because they also provide tools for software management. You can easily organize tasks. You can assign specific tasks to certain persons. You can see who has worked on what. You can make your code open and invite for collaborations. And it also provides versioning, which is the most important feature of Git properly. So if you're working on some kind of a code snippet, you put it on GitHub, and then you continue working on it, you change something, you again update the code on GitHub, and then you realize, oh no, there's a bug. So if you use Git, then you can just go to the previous version. If you don't use Git, then you have a problem. But again, teaching Git is probably beyond out of scope of this lecture. So just follow the tutorial to a software carpentry, and there you can learn how to use it. Final recommendation is document your source code. Software documentation is probably a daunting task, but if you follow the first 4 recommendations, then you are already on a very good way. You just start with a clean workspace. You have a hierarchical folder structure. For example, the one on the right, where you have a folder for the source code, a folder for the data, for the figures. And in this case, we also have a central entry point to the analysis, which is also an Markdown file called analysis. And if I would see something like that, I would be very happy. Because I look at that and I know from the beginning, I know immediately what I need to do to run the analysis. You should also include a README file and explain your repository a bit. So what does the software? How can you install the software? Are there any computational requirements, for example, related to the operating system or other versions of the software? How can you use the software? And also, how long does the analysis take? I had 41 articles in my study. Some of them were done after 2 seconds, and others took 1 week. And I didn't know that it took 1 week. And last but not least, you should also add a license, an open source license. So, for example, MIT license, Apache license, and so on. But we will take a closer look at licenses later. Yes, please?
So what would be the difference between like analysis, R&D, and the stuff in the code folder? Would it be like one calls what's in the other, or like what?
You mean if you have your code in your notebook?
Or, yeah.
I will come to that in a bit.
Okay.
So these are the 5 recommendations, which are not only relevant in academia, but also in industry, of course. I have some more principles and best practices that are more relevant in a scientific area or in scientific publishing. The first one is pretty obvious, it's sharing. So if you have your materials, you should share them in open, public, trusted repositories. But how can you do that? The idea is very simple. You prepare a package that is called Executable Research Compendium, ERC. And this compendium contains the open access version of the paper, open data, ideally the raw data. So again, no data manipulation outside the script, if possible. Also using open data formats. Open source code to run the analysis together with the data. And also details on the computational environment, such as the operating system we used, maybe the version of the software, and so on. Binder is a very helpful tool for this purpose, but I will come to that in a bit. So we put all that stuff in one package and store it in an open repository. And in these repositories, we also get a DOI. For example, on Zenodo, Open Science Framework, Done, Stride. So we put our materials there, we get a DOI, we can link it in our paper, and it's permanent. Speaking about DOIs, this is another best practice. So you should insert persistent identifiers in the published article that link to the data and the materials, underlying the results in the paper. And then you can add a supplemental materials section. For example, you can say something like, research data and source code supporting this publication is available on then the name of the repository and accessible via the following DOI, and then a DOI to the repository. Sometimes there are some legitimate reasons to restrict access to the materials to your work. Then it's fine not to publish the materials, but then you have to mention that for transparency purposes. For example, research data and source code supporting this publication is not available due to, and then you can indicate a reason. For example, licenses, data on human subjects, private or sensitive data, and stuff like that. So it is important to be transparent about that. So authors publishing source code that you reuse in your research also deserve some credit. So giving credit when you reuse materials is very important. So if you copy a text snippet from a scientific article into your paper and you don't cite it, it's plagiarism. It is actually similar with data, right? So if you use someone else's data but don't cite the data, then it's also some kind of plagiarism. But it's not seen as such. But it's important that we change a bit this culture of sharing and this culture of reusing. So if you reuse research materials published by others, you should also cite them properly. And this is relevant for data and for source code. And this is how an example citation can look like. Also mentioning the version. Of course, you cannot cite all the libraries that you use in your code. Of course, there are sometimes many of them, but you can cite the most important ones. I already mentioned licensing. So there's no open source software without an open license. And you maybe have heard already of Creative Commons as a license, which is often used for data sets and for research articles. But this license is actually not applicable to software. If you want to learn about software licenses, then I strongly recommend the website chooselicense.com, which is great help for the right software license. And they also provide an overview of conditions and permissions for each license. And based on the licenses, I created a spectrum of software licenses. It starts from the unlicensed to the which has almost no restrictions and conditions, to the GNU AGPL, which has quite a few conditions. And except for the unlicensed, the licenses below the arrow are copyright licenses, whereas the licenses above the arrow are copyleft licenses. The difference is that copyleft means that if you build on top of copyleft licensed research code, then your work has to use the same license again. This sounds a bit restrictive, right? So it sounds a bit like, in copyright, for example, it's different. You can reuse the code and use another license for that. You just need to cite or mention the original authors. But in copyleft licenses, this does not work. You have to use the same license again. But the idea with the copyleft licenses is to protect the work a bit. So you can protect your work from becoming commercial. And you can also protect your work so that other users can continue using your work, and that they can still modify it, share the work, and so on. And it's a bit of a reciprocal cooperation. So you use open source software, you provide open source software. But I personally prefer the copyright licenses, to be honest. So everything can do with that whatever they want. They just need to mention where this is coming from. But it's an individual case, I would say. There's no one size fits all. But again, if you want to learn more, choosethewebsite.com. Now I would like to continue with a little practical. So you are invited to follow me, but you can also just watch. That's up to you. First, I would like to show you how such an executable research compendium actually looks like. It's here. So this is basically the practical implementation of such an executable, or you don't see it. So this is basically the realization of such an executable.
Thank you. Perfect.
Okay,
Thank you very
thank
much.
you. I think I will just mirror my screen for a second. All right. So in our studio, I can just create a new project. So I copied the link from GitHub. I don't.
Your screen is not shared. I think you closed it somehow. I'm sorry. Can you maybe go back to Zoom? Yeah, it's not shared.
Oh, it's
anymore,
not
so you
shared at
just
all.
have to go to the app. I'm sorry for the inconvenience. It seems to shut down. I don't know why. Can you open it? Yeah, wider. I think it's here. Yeah, and then here. And also, I don't know which one you used.
It's, yeah, I only have one at the moment.
Yeah, I think you shared yourself. Maybe this one.
Yeah, that's fine. So I want to mirror the screen.
Okay.
And here under version control, I can also enter the URL to the GitHub repository. And as you can see, they also use relative file paths, not absolute file paths. And that's how I can, that was close. And that's how I can reuse this template for the own research. And here then I also have the folders with the code and the data and the figures. Here I have the R Markdown file. At the top, I have some metadata to make my research more findable. So I have the title, the author, some licenses. So I also have separate licenses for data, code, and text. The abstract, and then I have these code chunks. So as you remember, these computational notebooks mix text and code. So here I have a bit of text with some titles. Then this is followed by a code chunk. And I also usually use the first code chunk to load the libraries. Then I load the data. And then also data processing has an own code chunk. Visualization has an own code chunk. So this is one way to structure an analysis using such a computational notebook. And if I run it, then yeah, I get a PDF document which contains a variable and executable file. And this is what I can share with others. So that's very easy. What I actually wanted to show with this setup, because you're actually probably familiar with using Git, RStudio, and R, but I wanted to show that with such a simple setup, you can cover most of the recommendations and best practices that I showed before. So we are using open source software. So we are using R, we are using R Markdown, Git, and so on. We are using scripting languages for our analysis. We are using computational notebooks to have a narrative combining text and code. We are using Git as a versioning tool. We also have a documentation on Git with a clear folder structure. We have proper file names, which are also understandable for people who see it for the first time. We also have a README file, which is in this case pretty short, to be honest, but yeah, you can add more information if the analysis is getting more complex. We have licenses, so I mentioned that we have 3 different licenses for data, software, and code, because not every license is applicable to every type of research material. We also have citations, so I also cited the packages that I use in the script using the the references bib file. And yeah, I don't have a DOI, but that's not needed for such a template. And yeah, this is a very simple and basic way to cover most of the recommendations and principles. And this is a very good first step. Yeah, but what if others don't have R or RStudio installed on their local machines? So, or what if they don't have the time or the skills to work with that? And this is what brings me back to Binder. I will share the URLs in Mattermost. And you are invited to click on these links. Oh, that looks strange. I would recommend that you open as I did and actually see something like that. So this is a Jupyter notebook in a Jupyter Lab environment. And this is running in the browser on Binder. I can simply use the same URL, go to my Binder, and this is where I can add the URL. What I get is another URL right here. And this is what I can open in a new window, in a new tab. So I made a little mistake. Actually, I should have shared with you the link to the GitHub repository first, so you can create your first own binder. Yes, let's start with this one. So this is the link to the GitHub repository. If you want to, you can try it out by going to mybinder.com, mybinder.org, and paste the link to the GitHub to this field. And then you can copy this link in a new tab, open it, and then it takes a while to run. So you can also check the logs if you like, if you're more into these technical details. We also need to consider that my binder is actually not a commercial provider, so they don't have so much infrastructure power in the back end. It's more like a prototype. So if we are now 15 in this room and we all try to create a binder, then it might slow down a bit. So it might take a few minutes to run. What Binder does at the moment is creating a Docker file based on the information we provide in the GitHub repository. You might have noticed the folder .binder. .binder contains two configuration files. One is the runtime txt, which contains the R version, the date of the R version. The other one contains the libraries that are needed in the script. In this case, ggplot, reader, and weather metrics. And based on this information, that's enough. That's all you need to provide. Binder can create a Docker file to run the repository. Of course, the repository should contain some kind of a computational notebook, for example, a Jupyter notebook or an R Markdown file. Sometimes it can fail to connect to the event stream, whatever that means. But then you just need to just reload the page, and maybe it's working at some point. And this looks much better. And here we are. Here we can select RStudio. And what we get is the same environment that I had before on my local computer, but in the browser. The nice thing is I don't need to install anything on my local computer. I don't need R installed. I don't need RStudio installed. I don't even need to care about the libraries. I can just open the R Markdown file and work on that. So I can also modify it in the browser. You can just click on it and rerun the PDF document or the HTML in this case. And this is a very, very accessible way of providing reproducible research without the need to install anything. All right, now I want to get back to the two URLs. Okay, it's still creating the file. So now, as you can see, we have the same file as before on our local computer, but yeah, all in the browser. It's a bit like Collab, but yeah, open source. There was a question, so if I have the code in the computational notebook, why do I need another folder for the source code? It's actually up to you if it's really necessary to have a code, a folder for the source code. In this case, I have one. I also have a file in this code folder. It's just one function, but sometimes code scripts can be very complex and can have many, many source code lines. If you put that all into the analysis R Markdown, then you might lose the overview at some point. So I think that the computational notebook should be also a readable document regarding the code. So you can, what I usually do is I call the functions in the notebook, but the actual implementation of the functions is in a separate file, in a functions file. So if the people want to know more details about that, they can just go to the folder code, and there they can read the function. That's one recommendation, but it also all depends on the complexity of your scripts. Good. I shared 2 other URLs with you. The the 2 links to my binder, these 2, and I kindly ask you to open them in 2 separate windows, and you should get something like that. And you can simply run the code chunks. And you should get the plot. Actually. Oh, it's not working. This is what can happen to Binder. It's just a demo tool. Is it working on any computer at the moment? Yeah, you have 2 maps. That's very nice.
The second or the first thing?
So you have 2 tabs, and you render 2 codes, and you have 2 maps. And these maps probably look different, right? Does anyone not see it? I also have a backup slide in the worst case, but if you all have it, then I don't need to show it.
I just have one.
So, so it should look like that, right? You have these 2 maps. Good. So why are the 2 maps different? Any ideas? Sorry?
It's just the colors.
Well, the source code, is there any difference in the source code? No. But if the source code is the same, so why are the 2 maps different? How is that possible?
Magic.
Magic. Magic is one possibility.
I get a warning in one.
Sorry?
I get a warning in one plot, and the other one doesn't give me a warning. Yeah.
The what's different? Environment. Maybe the environment. So what I can do now, because it's not running on my computer, but what you can do is to click on this button, GitHub. You can click on this button, then you get redirected to the GitHub repository. And there you should check the configuration files. And maybe you will find something. Did anyone find something? Yeah?
The matplotlib, the different version.
The matplotlib library has a different version, right? So the 2 GitHub repositories use different versions of the same library. And this is something that we don't see if we just share the source code scripts and the research data. So if we have an R script, usually the R scripts don't contain any information on the software versions. And this is why the computation environment and such solutions like Binder are super important for open, because this might also be one of the reasons why the two maps that I showed in the middle of this lecture were different. Maybe that's the reason, we don't know. I didn't try out different versions of the libraries. But yeah, I just wanted to show you that considering that is very important for reproducible research. I would like to show you another example. Feel free to open this one. I'm not sure if this is working now or if it's too much for Binder. Nah. This one is another example. And I want you to do the following. You should just make a simple calculation, which is 1 divided by 5. Well, it's not running on my machine, but try it out on your, please. What is the result? Does anyone have a result? Not working? Still okay. So I want you to do this calculation 1 divided by 5 in one of the other notebooks and in the one that I shared the last one. In one of with the two maps, you can just add another cell and make this calculation 1 divided by 5, and also in the link that I shared, the last link that I shared. So this is the result of the last link. 1 divided by 5 is 0.2. If I run the same here, it's not working. 0. Why is that? You have an idea? Just wait a bit. Does anyone else have an idea?
Running settings.
Running set. Where we use the same way of entering 1 divided by 5. How can you check that? Well, you can look here in the upper right. And if we go to the older one, yeah, I cannot see it. It's Python 2. Not sure if this is what you also had in mind. Yeah. So it's at the end was the Python version 2 versus Python version 3. And apparently they made a change between the two Python versions. And this calculation is very simple, but it can mean a lot for our analysis. So this is also information that we need to provide in some way. We can't do so by providing a link to Binder, but we can also provide it as metadata if we don't have a Binder available. So it's just important that if others try to reproduce the results and figure out that there are these differences and they are wondering why, then the version is the first first indicator to follow.
Sorry, one question. What is the general way of documenting software and package versions in R in a project or GitHub repository? I mean, like requirements files and Python project that
Well, I would say that using this binder way of documenting versions is already quite useful. Because you have the version of the runtime with the date fixed, and you have the libraries. So this is basically creating some kind of a mirror of the R version. And from that date, it knows what kind of R versions, or what kind of library versions it has to use. And that's basically all you need to know.
but the package versions are not.
The package versions come from the mirror that was created at that date. Yeah, so if you have, if you used an older version of R, then you would change the date, and then you also have different versions of the libraries.
But this would then depend on binder, right? Or
Yeah, that's the configuration files for binder. Yeah.
meant more like a general. I mean, that's useful, of course, but I mean, that's just a general convention how to.
Or you can also specify it in the README file. Yeah, because they usually have how to install and also requirements, computational requirements. And that's where you can specify the versions of the libraries, the operating system, anything else that is needed. All right, I'm running a bit out of time, so I will rush through the next files. So, some lessons learned. The Executable Research Compendium is a package that contains the paper, the source code, the data, and the computational environment, which is, as we have seen in the practical, pretty important. The scientific article should contain a persistent identifier, a DOI, that links to these materials. So the GitHub repository that we had, we could put it as it was on Zenodo, for example, to get a DOI. This would be possible. It is important to cite software because researchers who spend time in developing packages deserve credit, and source code should be released under an open license because otherwise it's not open source software. So I also want to show some possibilities that come with open reproducible research. So you might remember 1665, the first journal was published. It was the Philosophical Transactions. And in the meantime, many things have changed on the world. So we have new interaction possibilities, we have new technologies, we have smartphones and so on, virtual reality, many advancements. But publishing at the same time has not changed so much. So we just have a digital version of the paper. That's it. And this brings me to another benefit of open reproducible research, which is some kind of knowledge valorization. So if we have the research article, the data, and the code, then we can do many things with that. So, and if we have this access to these materials, then we should reconsider whether the PDF document is actually the right way to communicate scientific results. Because as I said earlier, so describing data and code in the article is probably not so good, but maybe it's more like an interactive web application, the future scientific article. But there are some alternatives to this static way of communicating research results. One is called eLife. eLife is a publisher from the UK, and they focus a lot on reproducible, executable documents. So they do not only publish the scientific article, but also the code. And the scientific article in this case looks actually like a normal HTML version of the article. But in the upper left corner, we have a button saying Run Document. And if we click on that, then we get something like that. So for every figure, we don't only have the caption and the text, but we also have the code that creates this figure. And we can run the code in the window and reproduce the results. And we can also copy and reuse it, of course. Another application is the whole tail. The whole tail is quite similar to Binder. We can use whole tail also to create some kind of a computational environment by specifying the R versions and RStudio. And then we can load the data from Zenodo, from Dataverse via the DOI, and work with that inside whole tail. Yeah, we also get an RStudio environment where we can, as we did on Binder, we can also just run the code and create the PDF documents. And this is also the nice thing about Binder and whole tail. So if you create such a folder for Binder, you can also use it on whole tail. It's independent of the application. It's not like you need to create specific files for Binder that you cannot reuse somewhere else, but you can just reuse it for other platforms. There are quite a few applications, and it's a bit about what you need at the end or what you like. I created some kind of an overview of these applications in a paper, and I also checked for several properties. For example, whether they have an open license. So not all of these applications that are showed here are open source software solutions like Colab, for example. But yeah, I checked whether they have an open license or whether you can just install them on your local machine and reuse it or not. I also checked whether they use whether they support R Markdown or Jupyter Notebooks. Not all of them support both formats. So depending on what you are using, this will exclude already some applications. But yeah, fortunately, most of them at least support one of them. Then there are also some other features that might be interesting for users, such as discovering possibilities so that you can search for scientific articles and research outputs. Inspection, so you also would like to inspect the source code and the data set, for example. Some are just execution services. And manipulation, so can you also work with the data in RStudio or Jupyter Lab? And finally, substitution, so you can also substitute the data set by an own one and thereby replicate the research results. Another application is rather new. It's provided by the Group of Earth Observation. I'm not sure if you've heard of that already, but this is quite a big initiative. And what they recently released is the Geo Knowledge Hub. The Geo Knowledge Hub is also a web application where you can search for scientific research outputs. And this is one example. So you have a paper in an HTML version. And what they have is something that's called the knowledge package. And this is very similar to the Executable Research Compendium. So you have access to the data set. You have the paper itself, of course, but you also have the source code, the software, and so on. So everything is linked on one page, and you can just go there and reuse it, redistribute it, and so on. I would like to close this session with some things to consider, and maybe you want to discuss this in the break with your colleagues, with me, whoever, because there are some things to consider when it comes to open reproducible research. Because reproducing results can also mean that we reproduce errors. So how shall we deal with that? Others might become discouraged to collect data for replication. So if everything is available, maybe I don't want to collect data to replicate research results. I will always just reuse existing data, but maybe I will stop collecting new data. How shall we deal with that? Is open reproducible research the ultimate goal, or is it just a basis? And the basis for what? I showed you some opportunities, but what else is possible? And finally, reproducible research is not necessarily of high quality. So reproducible research can also be wrong, but we can check it. Good, to wrap up. So reproducible research refers to achieving the same results, using the same materials. There are some selfish reasons, and unreproducible research comes with a number of problems, and still open reproducible research is not common practice. accessible code and data is not necessarily reproducible. We saw some technical issues. We saw the importance of the computational environment. And fortunately, there are some reproducibility principles like the Executable Research Compendium and some tools like Binder that help us to overcome these issues. And once again, a reminder, tonight at 8, we will meet here to try to reproduce each other's workflows. So if you have something to bring to this evening session, then feel free. Otherwise, you can also try out someone else's results. So that's it. Before we close, so this was quite a lot. There are a lot of best practices. There are a lot of principles. And you don't need to do everything from the beginning. Just pick 1 or 2 of them, start, and in the next project, you can continue. Because as McKiernan said, openness is not all or nothing. Fully open research is a long-term goal, not a switch we should expect to flip overnight. That's, I think, a good closing statement, right? So thanks for your attention.
Thank you.
Questions? Do you have time for? No, we don't have time. Well, if you have questions, then we can always have a chat.
Notes.